Hello, everybody. Good morning, good evening. I'd like to talk to you about the cognitive status of simple and complex models in speech communication. So I'm going to talk about the cognitive status of models for 3 levels of representation in the linguistic system. That's phonetics, phonology, and morphology. And the case studies I'm going to talk about are organized in that order. I'm going to start with phonetics because that's where speech communication engages with physical reality. And it's the starting point for the language learner. Phonology, the grammar of sound structure, is more abstract. So phonology is asking, what is a possible word form and what is a possible phrasal form from the point of view of sound structure? Morphology, which is the theory of word formation, is even more abstract. It describes possible and impossible relationships amongst words in a language. And individuals learn each level by building on the previous level. They learn phonetics. They start learning phonetics even before they're born and make remarkable progress in the first few months after they're born. They're still learning morphology in adulthood. Now, the phonetic theory I'm going to talk about is the acoustic theory of speech production. And why start here? First, it provided a turning point in the study of speech communication. And from my point of view, it still provides a benchmark for a fully formulated theory with exact predictions. And Gunnar Font is responsible for seminal work in this area. And he was, in fact, the first recipient of the Medal for Scientific Achievement, which he was awarded at Interspeech in Paris. And my own sabbatical in Font's lab that year had a really important influence on my own intellectual development. Now, the centerpiece of this theory is a theory of vowels. And that reduces the core of the relationship between articulation and acoustics to a linear systems theory problem. So the source of the sound is the vibration at the glottis. And then there's a transfer function, which is characterized by the resonance of the tube in front of the source and also the radiation at the mouth. And then there are some simplifying assumptions, and they are very severe simplifying assumptions. First, the vocal tract is approximated as straightened out and radially symmetric. So it's closed at the sound source and it's open at the mouth. And then the sound wave is a plane wave along the length of the tube. And so the resonances related to the crossmodes are ignored. And if you make all these simplifying assumptions, the upshot is that the acoustic outcome is easily calculated using Laplace transforms, there's a beautiful development of that in Font's 1959 Erickson report. Now, the simplest case, which is the case of a neutral vowel, had already been solved in Chiba and Kajiyama in 1941. And Font built on that work, and he provides this diagram of what they showed. So the diagram is showing a mid-sagittal section for the uniform vowel, mid-sagittal section for the neutral vowel, and that is schematized as a uniform tube put right above the section. And then within each of those tubes, it shows these standing wave pattern for each resonance. So for the F1, the first resonance, that corresponds to the quarter wavelength. For F2, 3/4. For F3, 5/4. Now, Font carried out the generalization to tubes of variable cross-section, which was a very significant generalization and encompassed all of the vowels. Now, how simplified is this theory? So one indicator is that you can do the calculations on a 1980s model pocket calculator, as Font showed in a really sweet article in their working papers. And I looked up the model of pocket calculator that he was using and found an image of it. And there it is. That is a Casio 602P calculator. Another indication is that you can build a useful, interesting model by gluing together plexiglass washers and some other stuff you have around in your lab. And that's what Lindblom and colleagues did to study the effects of the radiation at the mouth. But there's some really realistic things about these simplifications. So what motivates these simplifications? First of all, the whole system has more damping when the glottis is open than when it's closed. So the closed phase dominates the acoustic signal. And another fact is that the cross-section of the vocal tract is small compared to its length, and the cross modes would have high frequencies. However, only the lower resonances are important for the perception of vowels, F1 through F3, and to some extent F4. And here's why. First of all, hearing is most sensitive in the F1, F3 range. I'm showing equal loudness contours for adults based on modern data. And as you see, the lowest part of both of those graphs is positioned at 250 up to just over 4,000 hertz. And that's exactly where the formants are. Another reason is that the vowel spectrum rolls off at higher frequencies. So even when the speaker is raising their voice, you'd be lucky to hear higher spectral peaks above the ambient noise. And I'm illustrating that with some narrowband sections from a study I did the year I was in Font's lab. And the high voice level there on the right does have a somewhat flatter spectrum. The third formant is much more prominent compared to F0, but above the third formant, it still rolls off very fast, and there's really not that much energy up at the upper end there. Now, there's been a lot of really important and impressive work after this acoustic theory of speech production, and some elaborations include a modeling of interactions of the glottis, using the theory of aerodynamic noise generation to model fricatives, and also integrating information about speech motor control. So the best current models are far more comprehensive and realistic than the original theory. But I think the original theory still reflects some deep cognitive insights. And one of these has to do with evolution. So we share our auditory system with other mammals, and that system was evolved to recover resonances, which provide information about what caused the sound. And in humans, the perception is most acute just in the range where the vocal tract produces a signal most efficiently. So that is a very nice evolutionary adaptation for speech communication. Now, another aspect of the theory that has a lot of cognitive insight is the dimensional reduction. So vowels can be very well characterized by three formants. So that means the vowel space is basically three-dimensional, and even a two-dimensional representation can get you a long ways. And the cognitive system is quite good at mastering three-dimensional mental maps, but four-dimensional maps are really difficult for people. But I think the most important thing of all is the fact that they used a linear approximation. So linear systems are much more learnable than nonlinear systems. This means that the acoustic signal can be inverted either to a unique functional representation or to a small number of alternatives, and similar gestures have similar results. So it turned out that the acoustic system is not really linear, but I think it is actually approximately linear. And this linear core provides scaffolding for learning the nonlinear aspects. Now, the next theory I'd like to talk about is the autosegmental metrical theory of phonology. And a central claim in this theory was that stress and intonation share key properties with word-level phonology. So in particular, each language has its own categories, and these must be learned. The system is combinatoric, so a small number of elements can be combined in many ways to make complex patterns. And both of them have effects at multiple time scales. So some regularities are local and others describe larger groupings. And then also both word level phonology and as well as stress and intonation have a certain simplicity. That is, not all imaginable patterns and constraints are possible. The ones you find seem fairly simple when viewed in the right way. So the goal of this theory was a unified account of the representation and realization of sound patterns that encompass both word-level phonology and phrasal stress and intonation. Now, one part of this theory goes under the name of licensing, and that is the theory of what contrasts are available and where. And just for example, here are some differences between English and Tokyo Japanese. So in the phoneme inventory, Tokyo Japanese has 5 vowels, and in English, depending on the dialect, you have 15 to 20 vowels, which means that a vowel position licenses more contrastive features in English. In Tokyo Japanese, geminates are quite common. However, in English, they're very rare. They occur only across word boundaries in words like Trans-Siberian. English has 6 distinct pitch accents, possibly more. Tokyo Japanese only has a single type of accent, high-low. In English, the domain for the pitch accent is the metrical foot. So that means every time you have a metrical foot, you get a chance to have a pitch accent. In Tokyo Japanese, it's the word, and in fact, pitch accents in Tokyo Japanese have nothing to do with the metrical pattern. And in English, the accents are a property of words in the lexicon. In Tokyo Japanese, they're a property of words in the lexicon. And in English, they're assigned at the phrasal level based on the pragmatic message that you're trying to get across with your phrase. Now, a second big part of this theory is the theory of phonetic realization. So principles of phonetic realization map phonological representations into articulatory gestures and hence into acoustic outcomes. And they're language specific, they're context dependent, and they must be learned. And that overturns the claim that they are universal and innate, a claim that was widely believed at the time in generative phonology. So here's an illustration of how the phonetic realization for tonal elements is very context dependent. And this is pulled from work I did with my wonderful collaborator, Mary Beckman. And the example shows effects of focus in downstep in Japanese. So the panels show a minimal pair of short phrases. In the left-hand panel, the first and focused word is not accented. So there's one accent on the second word. But in the right-hand panel, the first and focused word is accented. And then the next word is just the same. And as you can see, the accent on that second word is extremely compressed in the case where there was already an accent before it, and that's because of the downstep. The accent is there, but it is just the whole pitch range for producing that accent is very compressed. And in fact, the high tone in that accent is no higher than the preceding low tone. Now, once people found these effects with the implementation of tone, I and a lot of other people also started looking for similar effects on the phonetic realization of segments. And there are some very big effects, more than had been anticipated. And that is illustrated here with just a couple of clips from a recording I made of a Glasgow speaker. On the left panel, you have the two words, some music, and on the right panel, many worries. And you can easily see that the Z on many worries is very similar in appearance to the S on some, and it's really not very similar to the Z in music. The Z in music is far more voiced. And if you went to a little illustration of language dependence, you'll also notice that the R in worries is produced as a tap, and not at all like the American R. Now, I said that the same representations are used for both licensing and phonetic realization in autosegmental metrical phonology. And this shows how metrical strength and phrasing are represented by a hierarchical structure. So that's two intonation phrases, and the first one has a word that has two metrical feet, with the second one carrying the main stress, the stronger foot. Then sequential constraints are described by autosegmental tiers and associations. So here's an example of a structure for a Japanese word with a geminate consonant followed by a long vowel. As you see on that red autosegmental tier, the K is both the coda of the first syllable and the onset of the second syllable, and that is why it is pronounced as a single long K. And the O is also occupying two vowel structural positions, and that's captures the fact that it's a long O. So in the theory, all features for segmental and tonal substance appear on tiers, and they're associated with one or more structural positions. So if I go back to my earlier phrase, California, here I come, we can add a second tier to that to show one of many possible intonation patterns. And you'll notice that because we had 2 feet in California, we can have 2 pitch accents there. California, here I come. Now, Barry Beckman and I made a very strong claim about the power of phonetic realization rules in Japanese tone structure. So first of all, we claim that realization is computed left to right because speech production unfolds in time. And the realization of an element can be a function of its entire context, its neighbors, its syllable position, metrical strength, prosodic boundaries, but with significant limitations. That is, the reference to the context is local, as seen on the autosegmental metrical representation. And this theory was used to build intonation synthesis systems for commercial products for English and other languages. Now, again, there have been some significant advances since that theory was put together. So first of all, detailed experiments by speech scientists showed that memory traces of speech can be surprisingly detailed, much more detailed than the very minimized representations that we were working with in the 80s. So this points to models that have both detailed stored examples and the capability to generalize. And I'm mentioning there a review article in the Annual Review of Linguistics that I did on this topic. And modern computer systems have enough memory to implement this. So modern computer systems would be doing a lot more by table lookup and detailed representations of the known examples than was possible at that time. And another advance relates to the fact that the synthesis rules were kind of cobbled together. And in some cases, the contour shape was not that great, not very natural. But with new machine learning algorithms, it is possible to learn much more accurate and detailed F0 contour shapes that are, in effect, summarizing facts about speech motor control that we had no way of getting at previously. But I still think that there's some really correct aspects to this theory. So one thing is that people can and do learn language-specific, context-dependent, quantitative patterns for speech. And that was a big change. Showing that was a big change in the way people viewed the cognitive system. Another thing is that pronunciation reflects the interaction of factors at multiple time scales. And that's why hidden Markov models never achieved a human-like performance. They had no way of properly handling quantitative interactions of longer term and shorter, more local effects. And they had to model as lists of unrelated cases, things where people would see a generalization and use it. Now, there are some recent advances in deep learning that do allow variable timescale dependencies. LSTMs and transformer models do, and they do have the promise for doing much better. But so far, I don't see that they're yet benefiting from the theory of the limitations on the long scale factors. That is what's known about what can and can't occur. And autosegmental metrical phonology, again, actually had a linear core, just like the acoustic theory of speech production. And that's because the grammars are either context-free or finite state. And either way, they're provable results relating generation or producing to parsing or decoding or perceiving. And parsing can be formalized as matrix multiplication. And so the system is therefore linear. And linear systems are more learnable and therefore better from many points of view. So finally, I'd like to talk about morphology, the theory of word formation, which is what I've been mainly working on in the last decade. So people produce new words all the time. And the primary source of new words is productive morphology. So languages with highly productive morphological systems therefore have the highest rates of vocabulary growth. Languages like Vietnamese, much less. But even English morphology is more productive than you may think. And here are some words occurring less than once per billion words in Reddit, which is a social media site, and a billion words of several lifetimes of linguistic experience. So you are any individual person who's listening to this talk probably has seen hardly any of these words before. And those are words like blockbusterness, unnicknameable, anti-Yale. Now, what I'm going to call the old approach used rules. Given your choice of meaning, what complex form will you decide to produce? The claim is that you would select the rule whose structural description describes your input. And a very clear-cut example is vowel-epenthesis in the English plural. So if the stem ends in a consonant or vowel that is not strident, any non-strident voiced sound, you add Z. So P, Ps, 10, 10s, pad, pads. And I've left off the slide that if it's voiceless, the Z becomes devoiced to S. However, if it ends in a strident consonant, then you add schwa Z. So rose, roses, cash, cashes, and so forth. Now, starting in the 80s, there were very, very detailed studies that caused a big change in this theory. And now classic approach, which is due to Bybee and Seidenberg, Plunkett, Dell, and others, was based on findings that for a lot of morphemes, the results are not deterministic. Instead, they are statistically variable. So for example, if you ask people what the past tense of spride is, some people might think it's sprided, some people might think sprode. You'll even get people saying the past tense of bring is brang, whereas other people would say it's brought. And the variation is determined by cumulative effects of frequency and similarity. So an output pattern is most likely if many words that are very similar to your input have that pattern. It's least likely if few words have that pattern and they're not at all similar to your input. But how do frequency and similarity trade off? And very concrete predictive models were built. So one class of models use neural networks. One class of models used were exemplar models, such as Nosovsky's generalized context model. And in many cases, with very moderate assumptions, these are actually mathematically equivalent. Now, the old and classic approaches do have some common ground because actually they both treat word formation as a problem in categorization and decision theory. And I'm showing you that by graphing the plural rule to look like categorization in phonetics. So on the right, you have a very standard example of how voice onset time can be varied, and then you get a change in which phoneme is identified. And on the left, we also have some evidence on the x-axis, and the evidence is the stem end in a minus strident or plus strident sound. And then on the y-axis, you have the probability of the outcome. Okay, and for the English plural, that's either 0 or 1. So both graphs actually show sigmoids, but the voice onset data has a softer sigmoid. And in neural networks, the sigmoid functions, typically the softmax, are exactly the standard choice for the final decision layer. So for the softmax and for pretty much any other sigmoidal function, the step function will come out as the limiting case, and that's because of the free parameter controlling the slope. And then for the logistic and for many other sigmoidal functions, you have a second free parameter, the bias, and that could move the curve left or right. And so if it's a step function, it will move the threshold left or right. And this particular graph is actually a modification of the logistic designed to put the evidence on a scale from 0, that is no evidence, to 1, perfect evidence, for reasons that I'm going to come back to later. Now here's a successful application of the classic approach in predicting word formation, and that is a study I did with Lisa Dowdy-Hesterberg on Arabic plural formation. So Arabic has a non-concatenative morphological system, which you can formalize with autosegmental theory. It has at least 31 different non-concatenative patterns, and they compete with a pattern formed by suffixation. So plural formation is very hard to learn, and some people thought that really it's not learnable, that all broken forms had to be memorized. So we built several variants of a generalized context model using all singular plural pairs in a major Arabic corpus and carrying out a cross-validation and computing a baseline. We're using an optimal decision rule here, which means we're looking at what could people learn, not necessarily what did they learn. And it turns out that the broken plural is very predictable. And the best performing model considered only similarities to known forms that share the same CV template, and that means that it's learnable, provided that you can build on prior learning of phonological parsing for Arabic. But as I've said, I think that is a tractable problem. Now here are some more recent developments. So one is a rather complicated experiment on the competition between regular and irregular past tense forms in English. So the regulars have the ed suffix, and the irregulars fall in several well-studied lexical gangs. And the study used nonce verbs ranging from ones which are rather likely to have a regular past tense to ones rather likely to have an irregular past tense. The protocol involved collecting baseline data and then an interactive online game, which is referred to as an ESP game. And that's where you try to intuit what the other player thinks is the answer. And then if you both put out the same answer, you get a point. And then there was a post test. And the manipulation involved the strategy of the other player, who was actually a bot. And the factors were, first of all, the overall rate of regular versus irregular forms, and secondly, the type of examples the bot chose to regularize. So in the post-test, the players had been influenced by both factors, and that means that they did not just adapt the overall likelihood of a general rule. Instead, they carried out some sort of detailed update of their mental lexicon based on specific examples. And that result looks really good for the classic approach, that is the connectionist or exemplar approach, over an old, purely rule-based model. But there was a twist, which is that the baseline data, which are presumably the results of long-term learning, were best explained by a model that also had rules. So it looks like there's a mechanism for building up abstractions on top of remembering examples and evaluating similarities amongst examples. Now, another study reaching the same conclusion varied the statistical evidence directly on a scale of 0 to 1. And it is inspired by languages like Welsh, in which some stems have backwards number marking. So in English, we see one duck, we see several of them, we add a suffix ducks. But in Welsh, if you see a group of ducks, you use the bare stem, but if you see only one of them, you add an en suffix. And for English speakers, plural marking is obviously more familiar, and singulative marking is less familiar. So the experiment is a 2x4 design in which the dominant pattern was either plural marking or singulative marking. And this occurred either completely consistently or inconsistently. And participants learned the patterns by making guesses to advance towards a goal, which was the Welsh fairies' castle. So if they guess right, they move forward. If they guess wrong, they're sent back one step. And then at the castle, they're tested, both on the words they had seen and on novel words. So one result I'm not showing is that people remembered seeing examples to some extent, but not very well. The main result concerns the rate at which the dominant pattern was generalized to novel test items. And this is a set of violin plots which show, so those are smoothed histograms which are turned sideways, and they show distributions of individual behaviors for participants in the singulative dominant conditions in red and the plural dominant conditions in blue. And as you can see from the leftmost pair, if the input was perfectly consistent, both marking systems are easily learned. In fact, there's no significant difference between those two distributions. People varied a lot, especially for the less familiar singulative. And for the inconsistent conditions, some distributions are clearly bimodal. And the main reason is that some people had output patterns that were less consistent than the input. And some people even generalized the minority pattern. That was about 27 people in the study. So when we were modeling this data, we found that people used a decision function, but it's not sigmoidal. The function that fit really well was a double sigmoid. So like a sigmoid, it varies both in the sharpness and the bias of the decision function, but it has a flat part in the middle that allows it to generate the bimodal distributions on the last slide. And a sigmoidal function can't do that. So these results actually provide more evidence for a both-and theory, that forming an abstract generalization is above and beyond remembering examples, and that people vary in how much evidence they want to project a more abstract generalization. Now, a final note, what about semantics? So, of course, morphemes are associations of forms with meanings, and the research in the classic approach took a few obvious meanings for granted, such as the plural or the past, and focused on the selection of word forms. And that means that the domain of similarity that was considered was similarity in form. So can this approach be extended to areas of morphology in which the semantics is not so clear-cut? You know, can we find semantic categories and determine similarities amongst them? And does that help us predict what words people are going to make? Okay, so here is a study with Valentin Hoffmann and Hinrich Schütze, and it uses a modern machine learning method, a graph autoencoder, and is initialized with GloVe word embeddings. The goal is to predict which derived word forms will appear in Reddit. And you've already seen some very creative word forms. And it does actually succeed quite well. And it does that by finding semantic clusters. So here I have illustrated that with a 2D projection of the ESC and full families against all the against the full range of the data. So my conclusion is, in general, this appears possible. using advances in machine learning, but that's another talk. Now I'm going to come back to the cognitive insights of the classic model. So first, word formation patterns are learned as generalizations over word types and not word tokens. And they categorize the word types using decision functions based on the evidence. And type frequency and similarity relations both play roles in determining the outputs. And finally, the theory of categories and decisions that worked well for sound structure seems to provide useful precedents for semantic factors. So in conclusion, trying to pull all three cases together, in phonetics, phonology, and morphology, some classic models captured important cognitive properties, and that's why they succeeded as well as they did. And the two properties I've highlighted are linearity and categorization. And I think it's useful to start simple and use the simple model as a scaffolding for building a more complete and complex model. And in fact, human language learners probably do that. And language has probably evolved to exploit these learnable sweet spots. So that's it. Thank you all very much. Thank you all for participating wherever you are. And I really want to thank the ISCA community again for choosing me as the recipient of the Scientific Achievement Medal. It's really moving for me to receive this award. And I also thank you to the other researchers who created the foundations for my work and who've collaborated with me over the years.